Hi, today we are going to start a new chapter which is moving charges and magnetic field. So in the first chapter we have learned about electric field. What is that? We have a static charge, it can be positive charge, it can be negative charge that will create electric field around it. How can we find the value of electric field? We will place a 1 coulomb charge here. So we will see how this positive charge will interact with this 1 coulomb. So here it will be, this is plus 1 coulomb, right? Repulsive force. And this is how, in this way, we will be placing 1 coulomb at different location and we can get the value of electric field at that point. Similarly, for a negative charge, we will place a positive 1 coulomb here, that is a standard defined. Here it will be attractive force, plus 1 coulomb, plus 1 coulomb in this way. Similarly, so what is the cause here? Cause is static charge. Now for magnetic field, in the same way we have defined electric field, we can define magnetic field. The thing is here the cause is, what is the cause? Cause is moving charge. So here cause is static charge, charges at rest. Now charges which are moving will make magnetic field around it. So for example, moving charges. Moving charges. It can be any charge, positive or negative. So when a Q charge, that will produce magnetic field. When Q charge move in a space, that will produce magnetic field around it. And what will be the effect when a magnetic field is produced? So first I will explain the experiment done by Oersted. So he has seen, it is in 1827 I think, yeah. So he has seen that when he was sending current through a conductor, let's say this is a conductor and it is connected with a battery, a power source. When the current is passing through a conductor, he has seen a magnetic field deflection. Sorry, he accidentally has kept a magnetic needle, that is simply a magnet, a compass very near to this. So when the current was passing through this conductor, he has seen a deflection. What does it mean? That is, the magnetic field created by the conductor is present at this point and this has interacted with another magnet here and this magnet has deflected. I will explain you this in a better way. Let's say we have a magnet, we have a compass which is placed on the surface of earth. So it is orienting in this direction, north facing. Correct? Now how can we rotate this magnet? Let's say this is hanging on a string, so it is free to rotate. But when I am placing a next magnet here, south and north, let's say I kept a magnet on my hand and I have kept very near to this. What will happen? This will attract towards south. Now if I am placing, instead of giving in this direction, if I am placing north and south in this way, this will be repelled and will be going to the other direction. So who has interacted? One magnetic field or magnetic field produced by one magnet has interacted with another magnet and there was a movement. Similarly, when we have a positive charge here, when we have a negative charge here, this positive will attract negative and negative will come towards positive. Similarly, here what has happened? When current was passing through this, it has created a magnetic field here. Now this is a magnet. At this position, there is a magnetic field created by this conductor. So what will happen? This magnetic field will interact in the same way with this compass and that is the reason for the rotation. So this was the observation. So effect is, now this magnetic field created by moving charge that can interact with other magnetic field and also magnetic field has been defined in this way, like a property, a field that can turn a moving charge. I will explain it. So let's say we have a conductor carrying current in this way. Okay, so current is passing in this direction. Now when there is a moving charge, so magnetic field will be there. I will explain you what do I mean by into mark. So here in this case, current is going in this direction. I will make it in this direction. Okay, I will explain you all this, why I have changed the direction of current in this way so that I can kept the magnetic field as into. First, I'll explain you what is into and out. Into means magnetic field is into the plane. So into the plane means going through like this. Going through like this. Let's say we have a pen. So when we keep the pen having its nib facing the paper, it can hurt the paper, right? So it will damage the paper. So it will be into mark. Now coming out means, let's say we have a pen kept in this way. So it will be, we can see the pen nib, right? So that is coming out. So this one means coming in this direction. So from here to here. Now this one means from here into. Now the magnetic field produced by a current, by a source or by a current carrying conductor when a current is passing in this direction will be into. I will explain you in this video itself. Okay. So anyway, we have a magnetic field produced by a current carrying conductor here. Say for example. Now when a charge is moving in one direction, we will see that the charge will deviate from its direction, initial direction. In which direction it is moving? It is moving in this direction. Now the moment it enters a magnetic field, there will be a change in direction. Okay. Let's say for example, it has came to this direction, or it can also go to the other direction. This direction of force and everything I'll explain in the coming videos. But when a charge is moving in a magnetic field, that will experience a force. So how can we measure magnetic field? By measuring the force. Higher the force, higher is the magnetic field. I hope it is clear. I will repeat the whole process, whole scenario. Now, when a current is passing through a conductor, that is producing magnetic field around it. So when the current is passing through this, there is magnetic field across it. Everywhere there is magnetic field. Okay. Now, in that magnetic field, when we are allowing some charge to move, this charge will be deviated from its initial position, initial direction. The reason is the charge has got some force by the magnetic field, and that is the reason for turning of the charge. Okay, so we can measure the magnetic field in this way, that define the magnetic field in this way, that this is a field and it has a property of deviating or turning a charge. Okay, now I have explained you introduction part, definition, and how can we get the magnetic field intensity. So let's say there is some source creating a magnetic field here. So let's say this is into the plane means magnetic field lines are going in this direction. Now we have to measure, we need to measure the intensity of magnetic field at one position. Okay. So what we will do, we will allow a charge to move in this direction. Now the charge will deviate in this way. So there is magnetic field, right? So this is, let's say, Q1. Now we are allowing this, so Q1, let's say it is moving with a velocity of V1 now. Now I am keeping velocity same, but I am sending a different charge here, Q2. So Q2 is also moving at the same velocity of V1 that initially Q1 has moved, but the charge is different now, Q2. So when we have seen that the deviation was more. Now when I have changed Q2 to Q3 and the deviation is again more. So one thing is very sure, that the force exerted on the charge by the magnetic field is increasing when we are changing the value of Q1. So force is directly proportional to Q. Higher the charge, higher will be the force. First observation is made. Second observation, I have kept the same. So this one is first experiment, and the next experiment I am keeping here. Now I am sending Q1 at a velocity V1. It has got some deviation. Now the velocity I have increased to a new value. Then deviation was more. Then again I have increased it to a new value. Deviation is more. Okay. What does it mean? That here V3 is greater than V2 is greater than V1. So when I am increasing the velocity, force is more. So force is directly proportional to velocity. Now what else I can change? Now I have a magnetic field here, right? So that is produced by some current carrying conductor or moving charges. Now I have changed the current passing through the conductor. Let's say I have, so this into, right? So current is moving in this direction. So this current is producing a magnetic field here. Now I have changed the current so that I will get a new value of magnetic field, right? So when I have changed the value of magnetic field, I have changed the source. So what I have seen, higher the magnetic field, higher is the force. Okay. So force is directly proportional to magnetic field. So these are the experiment I have done. First thing is, so you can change the value of magnetic field without changing the value of current. All these things we will learn in the coming lectures. Magnetic field very near to the conductor will be more, here it will be less. So you can do experiment here and here, so that this can be a case where magnetic field is higher, this can be a case where magnetic field is lower. So keep Q1 moving at V1 velocity here, you will see higher deflection, but Q1 moving at V1, you will see lower deflection, which means higher the magnetic field, force is more. So anyway, these conclusions are made. So here third point is just changing the magnetic field, okay, either in this way or in this way. So we will bring everything into one equation. F is equal to, F is directly proportional to Q into V into B. So experimentally we have proven that the force is the constant. This proportionality can be converted into constant K Q V B, and the constant is 1. So Q V B. But force is a vector, you know. So this is a product Q V into B. So it has to be either vector product or scalar product. Why? There are two vectors involved here. Velocity is a vector, magnetic field is a vector. Magnetic field has a direction, right? So this have to be, LHS have to be vector. So you have two vector here. So two vector, when it is cross multiplied, that is vector multiplied, then you will get a vector. If it is dot product, then this will be a scalar. So I will keep it as vector. So what is the value? Magnetic field intensity can be measured as, so force we have measured. What is the value? QVP. QV cross B basically. So I will take V and B are perpendicular to each other, so that V QVB sin theta, sin 90 will be 1. So how can I get the value of magnetic field here? F divided by Q into V. Now can you define what is magnetic field? Magnetic field is 1 Tesla. Okay, magnetic field is measured with the unit of Tesla. So that is nothing but when a charge of 1 coulomb moving through 1 meter per second experiences a force of 1 Newton. Now the magnetic field at that position is equal to 1 Tesla. I will repeat it. So you substitute the value of F, Q, V as 1. So what will happen? If F is equal to 1, Q is equal to 1, V is equal to 1, then B is equal to 1. In this equation, F is equal to 1, Q is equal to 1, B is equal to 1. Correct? Now, what do I mean by that? So, when a charge of 1, let's say at some point, when a charge of 1 coulomb moving at a velocity of 1 meter per second, it experiences a force of 1 Newton. And the magnetic field at that position is equal to 1 Tesla, which means if you know what magnetic field at, if magnetic field at this position is 1 Tesla, then if you are allowing 1 coulomb to pass at 1 meter per second, so I am keeping this as 1, let's say magnetic field intensity is 1 Tesla, Q is 1 coulomb, V is 1 meter per second. So if all these are 1, then F have to be 1. Now, then the force experienced on this will be 1 Newton. Clear? That is the value of magnetic field. So we have a lot of equations coming up to find the value of magnetic field, but as I have defined magnetic field in this way, we have got one equation for magnetic field, and this is an equation for force, and this with this equation, with this value, you can even find the value of magnetic field if you know F, Q and V. Okay. Now I have explained to the third point, and the next point is magnetic field shape around a conductor. Now I have told you a moving charges produce magnetic field. Okay. So let's say we have a moving charge in this way. It can be current, it can be simply a moving charge. So let's say current is passing in this direction. Now it will produce magnetic field around it, right? So I am going to keep current in this way. Sorry, in this way. Current is moving in this direction. How can I get the value of magnetic field here? How we have derived the value, how we have got the value of electric field produced by a static charge? We have placed 1 coulomb here and got the value of force, got the value of force, got the value of force, got the value. At all the point we have placed 1 coulomb and got the value of electric field lines. Similarly, here with magnetic field, who will interact? With magnetic field, magnet will interact. Okay, so I will keep a magnet here. It's north and south in this way. And I will mark the direction. Okay, so at this position, when I am keeping the magnet, I will get the direction of magnetic field. Why? Every magnet will be pointing in the direction of magnetic field. Let's say when we are simply hanging a magnet here, it will be pointing towards north because that is the direction of magnetic field on earth, right? Similarly, around this magnetic field created by a moving charge or a conductor, the compass will be pointing along the direction of magnetic field. So at this value, at this point, we got the value of magnetic field. And here we will do the experiment, here we will do the experiment, here we will do the experiment. When we are doing the experiment and checking the value of magnetic field, we will get in this way. Which means, let's say this is current carrying conductor. So magnetic field will be in this direction, in this direction, in this direction, direction. What do I mean by that? It is circular around a current carrying conductor in this way. Okay. So when the current is going in this direction, this is a case of current coming in this direction. Okay. Now when the current is going in this direction, we have done the same experiment and we got that magnetic field is in this direction. Okay, magnetic field reverses the direction when the direction of current has been changed. Okay. Now, how we will get the direction of magnetic field? So, I told you in a current carrying conductor, magnetic field will be circular. Okay. Circular in the sense at this point it will be tangent of the circle. At this point, tangent of the circle. At this point, tangent of the circle. But tangent can be in this direction and also in this direction. And how we will get the actual direction now? So let's say current is passing through this direction. Now we will place our thumb in this direction. You can rotate your finger like this. Okay, like this you can rotate. Anyway, bending like this is not possible, right? So rotate your finger in a possible way and keep your thumb in the direction of current. Now at this point you got the direction of magnetic field. Here this one, here this one, here this one, here this one, here this one. So in this way. So here when the current is passing in this direction into the plane and here coming out of the plane. So here it is into, here it is coming from the plane. Now when current is passing in this direction, I am placing in this way. So into the plane here. And here it is coming out of the plane. This is very, very important. Make a note of it. Thank you.